My name is Tamás Fekete. I'm head of the Structural Integrity Group in the Center for Energy Research, and our main field of research are the so-called pressurized thermal shock calculations, which are a special type of accident calculations for the nuclear pressure vessels. First, I like to introduce you the research context, which will be followed by the concept of structural integrity and the concept for structural integrity calculations. And at the end, I will introduce you results of an industrial relevant case study. What are the large-scale pressure systems? They are mainly used in the energy and the heavy chemical industry sector. Let's see in a figure a part of a reactor coolant system of a VVR 440 nuclear power plant. It comprises from a reactor pressure vessel, the main coolant pipelines, and the steam generator. The whole unit has six steam generators. They are called six-loop type VVR reactors. The most safety critical part of the system is the reactor pressure vessel, which has a height around 11 meters, an outer dimension around 3.9 meters, and the wall thickness on the most relevant zone around 15 centimeters. The system is considered safe when it is damage and overload tolerant. The safety of the system is assessed many times during the system's lifetime. At first, during the design phase, with design safety calculations, which predict the so-called design service lifetime. But during operation, these calculations are called structural integrity calculations, and these calculations are based on real operating history and real data of the materials, which are assessed by the maintenance surveillance system and surveillance system. Let's have a look on the methodology of the design safety calculations. It comprises four types of quite complex calculations. The first are the thermal field calculations, which are followed by stress strain calculations and aging calculations and fracture mechanics assessments. The thermal field calculations are based on the classic theory of heat conduction. The stress strain calculations on the classic theory of strength calculations. Description of aging is based on empirical formulae, and the fracture mechanics calculations use mainly the global models for fracture mechanics. The coupling scheme is a staggered coupling scheme widely used in engineering calculations. The methodology of structural integrity calculations inherited their methodology from these type of design safety calculations, which are based and which has its roots on the early period of the 20th century. Now, at abstract level, structural integrity is a practice-oriented conceptual framework which has four aspects: the philosophical, the scientific, the engineering, and the practical aspects. The philosophical aspects are used to underpin the scientific theories. The scientific aspect cover the set of theories and experiments that support engineering application development. The engineering aspects comprise the applications and activities used for industrial calculations. And the practical aspects focus on the very, very practical aspects of industrial systems. Let's have a look on philosophy. You may ask me why philosophy is important for not only for me, or the question can be asked, is philosophy or can be philosophy relevant for any science? The answer is yes. It is because the methodology of modern sciences is rooted in philosophy. It is based on the analytic, so-called analytic synthetic method of Aristotle, which was worked out in ancient Greek. But it has become clear nowadays that this method has serious limitations. But current philosophical research has shown that a brand new modern version of the analytic method, which was also described first by the ancient Greeks, by Plato, is free of these shortcomings. This morning I forgot. And the key difference between the two methods is that the analytic method allows to open brand new questions concerning the fundaments of any theory, but the analytic synthetic method does not. It means that the analytic method allows a paradigm shift. Why is paradigm shift relevant for us? Because we have a theory which has roots in the from the beginning of the 20th century. We want to move this theory or their base to a modern thermodynamics-based holistic concept. The paradigm shift means that we move from a mechanistic, reversible worldview to a completely irreversible worldview. And these two approaches differ. But this worldview is very deeply rooted in the theories. Let's see the scientific aspects. From the philosophical considerations, it follows that modern continuum thermodynamics is an adequate physical theory to underpin the new methodology, because it is a field theory which is developed for time-dependent, dissipative, inhomogeneous systems with finite state change rates. And because dissipation is a common factor in various aging processes as well as in fracture, we expect that the theory will allow a unified treatment of aging, including fatigue and fracture. The equations of the new theory are much more complex compared to the good old one methodology. They comprise the equations of motion, the balances, general balances, the energy, and the entropy balance, the second law of thermodynamics, which is crucial in any thermodynamically based theory. And they are constitutive relations. And from the second law of thermodynamics, the generalized energy release rate comes out, which will be important for fracture mechanics. But the most important feature of the theory, that here the J integral is in general path dependent, which practically means that in calculations, the theory makes a difference between the local, the near field values, and the far field values. We have not much time to discuss this model, but I want to note that the path dependence of the J integral is a natural consequence of the thermodynamic theory. And I think this is not a bad attribute, but paves the way towards more reliable stability calculations for the future. And now we are moving to the industrial case study. The studied structure is a VVR 440 reactor pressure vessel with pressurized thermal shock transients. The transient has thermal part and the pressure part. The thermal part begins with fast cooling, followed by reheating and a slow cooling, while the pressure decreases first quite fast and then abruptly repressurization occurs with a high level of pressure, which then drops back and then decreases up to zero. The most relevant results of the calculations are as follows. We calculated the situation for the S manufactured for the new material and for an aged material. In both cases, the local or the near tip values are depicted with deep brown, and the far field values with dark blue. You can see that during during uploading, the J values are higher in the case of a new material and in the first phase of the transient, the local and the far field values are nearly the same, but are a bit and significantly different. And in the new material, the two values bifurcate when the repressurization occurs, and the most significant path dependency can be observed during unloading here. And this is the end state. This is the end state. The results show that the unloading effect exists, and it is proven by the calculations. This effect is called also warm pre-stress effect in the literature, and is an unsolved problem since minimum 50 years. Furthermore, our results are thermodynamically consistent and meaningful in the new framework, but they are uninterpretable with the original J integral developed by Rice. So these are my conclusions, and thank you for your attention, and I'm waiting for questions.
Thank you.